All right, so you've written some code. It works, it passes the tests, but you get that nagging feeling, right? Like, is this really the best way to do this? Well, today we're going to totally unpack what best even means in the world of computer science. Because, spoiler alert, it's not just about getting the right answer. It's all about how efficiently you get there. So yeah, let's get right into it. So here's our game plan. We're going to start with the basics. What is good code? Then we'll look at why just using a stopwatch is a terrible idea. From there, we'll build up to how the pros actually analyze code before they even write it, get into the language they use to talk about it, and finally, see why this whole thing is a massive game changer. Okay, so Section 1. What is good code? Before we can measure anything, we all have to be on the same page. Let's define our terms and figure out what our goal really is. First up, you've got the algorithm. Think of it like a recipe. It's the step-by-step instructions for solving a problem. It's not Python, it's not Java, it's not C++, it's the pure abstract idea behind the code. The program you actually write, that's just you following the recipe in a specific kitchen, using specific tools.
And, if the algorithm is the recipe, then the data structure, well, that's how you organize your ingredients. It's your mixing bowls, your spice rack. Are you throwing everything into one big pile, or are you organizing it neatly in something like an array or a list? The way you structure your data is absolutely key.
So here's the thing. For any problem you can think of, like, say, sorting a list of numbers, there are practically infinite ways to solve it, infinite algorithms. So how do you pick? Which one is the best? That's the core question, right? How do we find a way to say, objectively, this algorithm is better than that one?
When a computer scientist says better, 99% of the time they mean more efficient. And we usually break efficiency down into two main things: running time, literally how long it takes to run, and memory usage, how much RAM it eats up. Now both are super important for sure, but for today we're going to focus almost entirely on running time.
All right, so if we're focusing on time, what's the first thing that pops into your head? Probably just timing it, right? Let's call this the stopwatch problem. It's intuitive, but as we're about to see, it's deeply flawed.
Yeah, this is what you'd call the experimental method. It's super straightforward. Step 1, you code up the algorithm. Step 2, you throw some data at it. Step 3, you hit a timer and see how long it takes. Makes sense, right? It feels practical, hands-on. But oh man, it is riddled with problems.
Okay, let's just tear this whole stopwatch idea apart. First off, you have to fully implement the algorithm just to test it. That's a ton of work for something that might turn out to be a bad idea. Plus, you can only test it on a few inputs. But the biggest problem, the real deal breaker, is that your results depend entirely on your setup. Your fancy new laptop is going to run circles around my old one. How can you possibly compare my algorithm's time to your algorithm's time if we're running on different machines? You can't. It's not a fair fight. It's not scientific.
So clearly the stopwatch is out. We need a better way. We need a general methodology to analyze the idea of the algorithm in a way that's totally independent of the computer it runs on. Exactly. The goal is to develop a method to evaluate an algorithm's efficiency that is completely independent of the environment. We're looking for a universal truth about the algorithm itself, not just how it performs on one particular Tuesday on one particular machine.
Then our main tool for this is something called Pseudo Code. It looks kind of like code, it smells kind of like code, but it's not real code. You can't compile it. It's a mix of natural language and programming concepts. It lets you sketch out the logic, the loops, the if statements, without getting bogged down in all the fussy syntax, like where to put the semicolons. It's all about the logic, nothing else.
Okay, so if we're not using a stopwatch to measure seconds, what are we measuring? We count things called primitive operations. These are the absolute basic rock-bottom steps a computer takes. Assigning a value, doing a simple bit of math, comparing two things. We're not measuring how long they take. We're just counting how many of them happen. This gives us a standardized way to talk about the total work an algorithm has to do.
So we've got our strategy. Use pseudocode to count the number of primitive operations. Awesome. But now we need a language to actually describe our findings. And that brings us to the absolute core of this whole topic: asymptotic analysis and the only, big O notation.
Now, here's the key insight. We don't actually care if an algorithm takes, say, 5 operations or 50 operations for a tiny input. What we're obsessed with is how the runtime grows as the input gets bigger. If I double the amount of data, does the work double? Or does it square? Or does it explode into some unimaginable number? We're looking at the trend, the growth rate, as our input size, we'll call it n, heads toward the limit, towards infinity.
Okay, don't let the math on the screen scare you. The concept behind big O is actually pretty simple. All we're doing is finding an upper bound for the growth rate. Think of it like a ceiling. We're saying that as our input n gets really, really big, the number of operations our algorithm takes will never grow faster than some other, simpler function. It's a way of describing the worst-case scenario for our algorithm's performance.
So in the real world, we use a couple of rules of thumb to make this way easier. First, we drop any constant multipliers. So if an algorithm takes 3 times n squared steps, we just call it O at n squared. We don't care about the 3. Second, we drop any lower order, slower growing terms. So if you have 8n squared plus 5n, we just call it O of n squared. Why? Because when n gets massive, like a million, that n squared term is so huge that the 5n part is just a drop in the bucket. It becomes totally insignificant. We only care about the fastest growing part of the equation.
All right, I know that was a lot of theory. So now let's get to the big question. Why does any of this actually matter? What's the real-world impact? Well, you're about to see just how staggering the difference between these growth rates can be.
Let's take a classic example, insertion sort. Now, if you give this algorithm an array that's already perfectly sorted, that's the best case. It's super fast. It just zips through, checking each element once. We'd say that's O of n, or linear time. But what if you give it an array that's sorted in reverse, the absolute worst-case scenario? Now, for every single item, it has to shuffle a whole bunch of other items round. The workload explodes, and its performance becomes O of n squared, or quadratic. See? Big O gives us the language to talk about this difference very precisely.
And this right here is the whole point. Look at this table. In 1 hour, a good O(n log n) algorithm can chew through a problem with 7 million items. That's pretty good. But an O(n squared) algorithm on the same computer in the same hour, it can only handle about 40,000. And look at the bottom. The O of 2 to the n algorithm, after a full hour, it's still struggling with a problem of size 31. 31. That's it. It is completely and utterly useless for any real-world problem. This is why they say a better algorithm on a slow computer will always beat a bad algorithm on a supercomputer.
So what's the big takeaway here? Understanding this language of growth, thinking in big O, it's not just some boring academic thing you have to learn for an exam. It is a fundamental tool for any serious developer. It changes how you think. It forces you to move beyond just asking, does my code work? And start asking the much more important question. How will my code perform when the input size is 1 million or 1 billion? How will it work when it really truly matters?